Okay, so several years ago, I started drawing a lot on my iPad and sketching and painting, and I would go outside and draw a picture like this. And at the same time, I often also take a photograph at the same time it's a picture in case I want to work on the picture more later. But later I also look at them and think, well, notice that there are differences between what I drew and what I saw, what I see in the photograph. And my first thought is, well, it means I'm not a good artist. But then I actually go outside and look at the picture on the cell phone screen at the same time as looking in the world, and notice actually the smartphone also doesn't really capture the real world experience. The mountains off the distance feel smaller in the picture than they do in the real world. And so we try to develop one research system with the goal of helping people adjust the sizes of objects and photographs to match experience better. But we had a lot of trouble when we were doing this. And it felt like we just don't understand perspective well enough to really figure out how to do this stuff. And so that brings me, this is the subject of this talk. I spent a lot of time thinking about it after that. And the question I want to discuss here is, how do humans perceive perspective in pictures? So this is a human visual perception talk. It's not a computer vision talk, but I think the ideas here could eventually be useful for computational photography and for art. So perspective, I think in terms of projection, you have some geometric arrangement of objects in the real world, and you have to decide how to arrange them in 2D. So a camera might choose one arrangement or depiction of objects geometrically, and an artist drawing might choose a different arrangement, or might choose the same. But you have these choices to make about the 3D arrangements of the objects in the world in the 2D image plane. So the conventional thing that we all learn is linear perspective. So this is what I learned in school, this is what I used to teach in graphics classes. And I think we're probably all aware, the way it works is you set up an image plane, you set up a center of projection. For each point in the world, you draw a straight line from that point in the world to the center of projection, intersect it with the image plane, and that determines the color at an image point. And so the idea is then if you put your eye at that projection, then the colors of the image plane that the viewer would see would be the same as if they were just looking out into the world through a window. And most of our photographs are linear perspective in some way. So our cameras have kind of built in, we have vanishing lines and all the familiar features of linear perspective. So it's very widely used, very common. And it's kind of taught as like the right way to do perspective. It arose in the 15th century with Brunelleschi's development, and then well, he was the first one to kind of build a linear perspective apparatus, and Alberti sort of wrote it down for the first time, such as the familiar rules of one-point perspective. And then when the Italian Renaissance, they started to use it as a tool and to experiment with lots of different ways to create images using linear perspective. So, but since then, there's a term that comes called correct perspective, which originally means just the correct way to apply linear perspective. But when you read a lot of the literature, the way people talk about it, there really seems to be an assumption that linear perspective is the correct perspective. And this assumption kind of takes a few forms. So first is this idea that if you look at this, your eye is at the center projection, then it's like you're looking through a window. So therefore it should reproduce the experience you see in the world. There's the idea that this is what artists do. Artists use linear perspective to create realistic images. And most central to the perception goals of this talk, we as human viewers interpret images as though they are linear perspective images or approximations to it. And there's a lot of problems with each of these ideas, which I'm going to sort of breeze through a little bit. The first is that when we take linear perspective images, we have lots of kinds of distortions. And I'll focus on one, which is the familiar case of marginal distortion. This person's face looks distorted. The spheres in the lower right corner of the image also don't look like spheres, or they look stretched like stretched versions of spheres. And this has been known for centuries. It's an old problem from the Renaissance. And one of the explanations that sometimes you hear is that marginal distortions come from not viewing at the center projection. If you viewed at the center projection, you wouldn't have these marginal distortions. But that begs the question, where is the center projection? So to view this picture correctly, you should be sitting at the center projection. Where is it? Well, I would have had no idea how to figure this out before I started looking into it. Maybe photographers know, but basically for this image that I took on my iPhone in the default zoom mode, the viewing distance is essentially 3/4 of the image width. So let's say, I don't know, it's 2 meters wide, or suppose it was, let's say your eyes should be basically about a meter or two in front of the picture. If your eye is not currently 2 meters in front of that picture, then you were viewing it from the wrong position, according to the theory of linear perspective. So obviously, this is not how we really view pictures. We view pictures, we walk around, look at them from different focal centers. We look at giant faces projected on billboards or huge landscapes projected onto our cell phones. But this idea that we view from the center projection is really not true. It's just not how we look at pictures at all. In fact, if you look at a picture from the center of projection and you have both eyes open, you have normal binocular viewing, then you will still see distortion. So this idea that you should be viewing pictures from the center of projection is something that almost never happens at least for wide angle pictures. So it's really the rare exceptional case to like only open one eye and be in the right spot. So there's also this idea that artists use linear perspective, and this isn't really true at all. One source of information, Martin Kemp, the art historian, did a little survey of one particular collection of classical paintings, and he found that only 3% of the artists strictly applied the rules of linear perspective, although some of these pictures could have still been accurate according to linear perspective. Moreover, there are many artists throughout history, including famous ones like Da Vinci and Turner and David Hockney, who start out rigidly following the rules, and then they see shortcomings, and each of these people has written quite a lot about the shortcomings of linear perspective as a tool for making pictures. And if you start to look at examples and think about them, you can see that actually it's really not widely used. So for example, this is a famous example of Raphael's School of Athens, where the architecture follows one point perspective. But if you zoom in the corners of the picture, according to linear perspective, you would expect these globes, these spheres, to be stretched in image space with an aspect ratio of 1 to 1.2, and they're not. But even more, if we look at the faces, they all look normal, whereas linear perspective would say the faces should also be stretched in a similar way. So, and I've never seen classical paintings with faces stretched like this. So this really says that artists do not strictly apply linear perspective, especially for wide angle pictures. Instead, as Kemp says, linear perspective is a working tool that delivered convincing results when used in a pragmatic manner without following the rules slavishly. So it's a tool that you can use making pictures, but it is not the correct set of rules or the only set of rules. And like I said, more broadly, linear perspective is a historical rarity. We've been making pictures for 45,000 years at least, and only since the invention of photography are we seeing lots and lots of strictly linear perspective pictures. There's many other ways to make pictures, and really we want a perceptual theory that ultimately could encompass all these different ways to make pictures. So in short, linear perspective alone, at least in the sense of a single linear perspective model with a single center projection, doesn't really explain either how we as humans perceive art or how artists work. And so it's really short, it's incomplete as a theory or unsatisfying. So now I want to suggest an alternative theory or an extension, if you will, of this idea. And I want to first motivate it by some relatively recent information about how eye movements and fixations work in the real world. Like we've known for a long time these things are important, but we're just starting with the past decade to really understand just how important they are to human visual perception. So we look at in the real world. So this is a picture I took near my house, and you can look around. We have more than 180-degree field of view with binocular vision. But you can also, if you look at any specific spot, you can see things in lots of detail. So when I was standing here, I can look at the street signs and I can read them from the spot, even though they're tiny fraction of the field of view. And this is what, as I'm sure everyone knows, is a consequence of foveal vision. So the direction you're looking at straight, you see lots of detail. Everything else is reduced amounts of information. And one thing I hadn't really appreciated is that the foveal part of our vision is a really, really tiny fraction of it. So the conventional rule of thumb is you hold out your arm at arm's length. The angle subtended by your thumb is basically the size of the fovea. So it's a really tiny fraction of all of the things you see around you. And to illustrate its importance, look at, say, one of the street signs. I don't have a cursor here, but pick one street sign and then try to read any of the other ones. And I don't think you can do it. If you try to read anything while looking somewhere else, like you really cannot read anything if you're not looking right at it. And there's exceptions if the text is enormous, but in most situations, to read something, we have to be looking right at it. Look away, you can't read it at all. So we really, in order to see things, we have to look right at them. Now I want to give another demonstration of how much you can get in a short amount of time. So stare at that red dot for a second, and I'm going to show you a picture very quickly. So you had 1 second to look at that picture, and hopefully you saw some object or had a sense of what was in there. I don't think you could see all the detail, but hopefully you could see some sheep and some grass and stuff like that. Oh, I hope, yes. No, you didn't see anything? Did anyone else that, I don't know if it, no, okay. Let me just try that one more time. Now it's a little bit late since you've already seen it. I see that the timing is different between here and there. So, well, I don't know if maybe this is not the best example, but there's lots of evidence that you can look at something and see what's there, recognize the shape you're looking at right away without having to study the whole scene. And this makes sense from a survival point of view. It's not like you walk into a room, look, with your eyes everywhere, and then understand what you're seeing. Every eye movement, you get information about the world. And the argument is that this is going to be the same for pictures as well. So here's one more demonstration. And again, hopefully the video will, the pictures will, the timing will work out, I mean. So what I want you to do is look at this picture and see if you can notice anything odd about it. And I'll give you a little time, and hopefully it'll be visible here as well. And just you look around and see, and then specifically anything sort of non-photographic, anything that you wouldn't expect from a normal picture. So I hope that came through, but essentially what you should be seeing there, this is actually a video, and most of the picture was changing. That surprising at all, what you saw? So if you look at parts that are changing, I think that's a little tricky to find. If you stare at something with it changing, you can see it changing. But if you look at anywhere else, you're unaware of the change. So this is an example of change blindness. It's something where we see things that we're looking straight at. This is an example with the gorilla on the basketball is another famous example you might have seen. When you're looking right at something, you can see it, what's happening. When you're not, often we're unaware of the changes that are happening. And moreover, we're unaware that we don't know. This is called the illusion of awareness. We're unaware that we think we see everything around us, but we're really only seeing tiny portions of the world, or tiny bits of information, the things we're looking at, and large change in peripheral vision. So this means we can have the feeling that we're standing in front of a painting and taking the whole thing in, and we believe we're seeing the whole thing, but we're really seeing only tiny bits at a time. Okay, so that's with that background, then how does that apply to pictures? So you see a picture for the first time, you fixate, let's say, in the center, you get some information about the middle of this scene, and some information about the shape. Let's say fixate on the right, and then you see these fellows, leaning on this bench, get some shape information about them, fixate someone else, see the skyline, and ultimately, with enough fixations, you build up a picture, build up a sense and awareness of what's going on in the picture. And so the observations are, each of these glances, we are perceiving shape. We are interpreting the picture at each glance. We're not waiting until we've seen the whole picture to interpret shape. And these interpretations are usually stable over time. We don't change our shape perceptions based on stuff we saw later. These guys look the same the first time you see them and after you see the rest of the picture. And so the core hypothesis I want to propose here is that each fixation has its own perspective. That is, when you fixate in the lower right corner of a picture, you treat it, you have information about the area around that and context from the rest of the picture. You essentially treat that as if it's like a little picture itself, its own separate linear perspective projection with its own optical axis, and interpret the shape there accordingly. Then when you fixate on a different part of a picture, that is treated as its own little picture, its own little linear perspective, also centered at that new location. So that's the idea. And so again, the idea is your eye moves over the picture, you get information from different parts, and each part has its own linear perspective, and then these things are somehow going to be integrated together, or information is combined from them in a way which I don't have a lot to say about. And this applies to any kind of picture throughout, human history, even though the manifestation may be different. So that's the hypothesis. And now I want to present a set of whole bunch of pieces of evidence that I think support the hypothesis. And also these can also be seen as examples, evidence against pure linear perspective in the sense of a single central projection for an entire image. So the first observation I want to make about perspective specifically is the notion of locality. And that is that a lot of our shape perception, or maybe most or all of it, doesn't depend on where you are in the image or the content. So with these two fellows laying on the bench on the right of that image, if we completely change the context around them, put them in the center of the image, then I would think, we will perceive them as having the same shape. And this is definitely not true for a linear perspective. But essentially it means you look at them, you see them, you get their shape, and then that shape never updates. It's just based on the local information with a single fixation. Now, not everything is local. There's lots of arrangement, perspective information we get from the global context. So one point here is that shape is local and scale is global. So these two people, I don't have a pointer here, but the fellow in the center and the fellow in the lower right, they look like they have the same shape because they have the same appearance, but their scale looks very different because that depends on contextual information in the image. And so as a result, we have collage art. You can cut things out and move things around in 2D in a picture, and things will not look distorted. They'll look like normal shapes no matter where they are in a picture. It's just the relationships that depend on the global context. But shape is really about the local region of space. So this aligns with the idea that each fixation has its own perspective. And artists can compose lots of individually linear pieces into all kinds of different arrangements. Now, I want to use distortion, and using it a lot as a source of evidence for perception here. And when I say distortion, I mean something specific. People use this word to mean a few different things. So what I mean is it's about perception. It's about how people perceive things. We would perceive the shape, this depiction on the left, as being a distorted version of a real shape. So you might imagine what the real shape should look like. You can recognize it's not the thing that not the way it should look. And this is not about optical distortion or anything like that. And the observation here is, again, it's local. Shape perception is local. A sphere should look like a circle no matter where it is in the picture. The way faces should look don't depend on where they are in a picture. Here's an example that breaks where we don't recognize that distortion. These four individuals are seated in ways it looks like they're facing away from each other. This is a wide angle linear perspective photo. And yet it looks like, and yet they were actually photographed facing straight forward. So linear perspective gives us, we don't perceive this according to what linear perspective says. But again, also if we crop the picture and only focus on one individual, our perception is unchanged with respect to whether that person is, person's shape and the facing direction. It doesn't depend on where they are in the picture as linear perspective would. So we can formulate that prediction into a rule for distortion and projections. And this actually is something proposed in a paper from 1995 that objects should look as if they're viewed directly in the middle as they would in the middle of a photograph. And this exactly lines up with fixation dependent perspective idea that if you don't want things to look distorted, you should render them in such a way as if they're inside near the center of a linear perspective photograph or anywhere in a non-wide angle photo, and then they will not look distorted. And so this essentially is what would the fixation dependent perspective hypothesis would predict. Impossible objects and perspectives are another interesting case where each fixation of the object looks normal and sensible, but they don't. So you keep trying to make sense of the different fixations. They all individually look fine. It's the integration process that breaks down. And the illusion kind of goes away if the whole object is visible within a single fixation. And of course, the illusion becomes more compelling if the fixations are more realistic. So within computational photography, some of the best ways to create projections are content aware and adaptive. And I'll just point out one or two of these methods. There's a paper from Rob Carroll 9, where an extremely wide angle photograph and then perform a numerical optimization for a warp of that photograph that looks much better, much less distorted. And they do it by optimizing terms that correspond to special cases of what I just described. That straight lines should become straight lines, spheres should appear circles, and empty regions, we kind of don't care what happens with them. This is a more recent paper that runs in real time on a smartphone. It just does face detection and applies a perspective correction just to faces. The spheres in the lower right corner are still distorted. And in fact, this method is running on Google Pixel phones now. So if you have a Google Pixel phone and you shoot in the ultra wide mode, then as I understand it, it will do this linear correction, as illustrated here by Andrew, whose face is undistorted, but the straight lines around his face have been bent. And this is a photo on a Google Pixel. There's lots of his examples throughout art history and in computational photography of multi-perspective projection of, like here where Dante's face appears to be imaged head on, whereas his robes are sort of imaged from below. This is a nice example from Frater John's holiday card from December, where his family is photographed in these different cubbies. And the way this was produced with a separate photograph for each cubby, which are then laboriously composited together. So in the end, this picture essentially has one separate vanishing point and one separate center projection for each individual cubby, and yet it looks fine. It looks like a normal set of cubbies. You might, the walls don't seem flat; they seem trapezoidal, but aside from that, it looks totally fine. And I would really argue with the fact that almost all of our wide-angle imagery in classical painting is multi-perspective, in that faces and spheres are rendered as if they are viewed head-on, as if they are the centers of linear perspective imagery and not at the corners of a one-point perspective view. Now, the last bit of evidence on wide is a little more subtle, but there's been a lot of work in the human vision literature and the vision science literature where they attempted to resolve this contradiction of linear perspective, that of why it is that you view pictures when you're not at the center of projection. And the hypothesis they tested was that viewers correct for not being at the center of perspective, center of projection, mentally unwarp the image. And so researchers did many studies with different people viewing pictures from different points of view and different viewing conditions. And particularly this paper by Dhanraj Vishwanath that's really nice, where they asked people, does the sphere here look like it's too wide or too narrow under different viewing conditions? And what they concluded was, out of all this body of literature, is that people do not compensate for center projection. They don't interpret images as if they're the center projection. What they do compensate for is viewing slant. So when you see a large picture and you look at an object in the corner, you sort of treat that object as if it's unslanted. You sort of flatten it with respect to the view direction. It's local for wherever the object is in the picture. It's not the global adjustment you would expect with linear perspective. And so again, this aligns with this. This is exactly what we predict according to the theory that I'm proposing. So this theory I'm suggesting that we interpret each part of a picture as though it were a linear perspective picture and then somehow combine them is consistent with different sources of evidence that are not consistent with linear perspective. It's consistent with the idea of vision at a glance, that we interpret each picture and each fixation. We don't use information from later on to change our interpretation of shape, with weird exceptions that are important here. It's consistent with the idea of locality, that shape does not depend on other information from a picture like COP or the size of the picture frame. It's consistent with which, locality includes this notion of marginal distortion and the local slant stuff I just summarized. And it's also consistent with the fact that we have throughout our theory and computational techniques, multi-perspective projections where different parts of pictures can have their own projection and still look fine, both again in photography and in art history. So in short, when you see a picture, you look at different parts, you interpret each part with its own perspective, and information between these is somehow combined. And I guess now I guess I'll just briefly mention there is this last thing of somehow this information combined. I do not have a good explanation or theory about this. I think this is future work, but I will say I feel in the brain, I think that there's at least three three separate representations that all coexist in the brain. There's the retinal image you see with your eyes, there's the fixation level shape that you see at a single fixation, and then there's this information that somehow combines them and can recognize that if you look at a glass of water that has an object in it, like a real glass, you can recognize that the object looks bent and broken in the current fixation, but you can know that it's not actually bent. Or when you see a distorted face, you can know it's a depiction of an undistorted face. So to summarize, this notion of linear perspective that we're all taught in school and that we are taught is the right way to make pictures and how artists work, it doesn't really explain any of these things. It has many shortcomings. Many people have known this for a while. I think it's fairly obvious that doesn't really explain everything, but there hasn't really been a replacement for it or a theory that can explain how people make pictures or how perception works. And so that's really what I've tried to do here, is to propose a theory that could eventually explain how perspective works. There are many different hypotheses to test here and to evaluate, and I have a student now working on testing some of these ideas. And I think that ultimately these ideas could motivate better techniques for understanding art history and for interpreting paintings in our artistic practice and teaching, and also lead to new photography algorithms that let us make pictures in more expressive ways. Thank you.
The second presentation, is on semi-automated colorization, and it will be given by Hernan Carrillo in collaboration between Bordeaux University, CNRS, and Waseda University. Hernan, would you like to share your screen?
Yeah, sure. Is it sharing right now? It's okay?
Yes. Yeah.
Okay, perfect. So let me know whenever I could start.
I think you can start. Yeah, thank you.
Okay, so hello everyone. My name is Hernan Carrillo. Today I'm going to present in our work called diffuse art, enhancing linear colorization with the conditional diffusion models. So let's begin with the presentation. So the motivation of this work, mainly, well, first of all, what is linear colorization? Is the process of adding visually pleasant colors to monochromatic line drawings, as shown in this example figure, where color schedules are used to colorize this line art, for example. This task is essential in the workflow of many industries, like animation and graphic design. However, the process is time-consuming and currently is still done, most of the cases manually, which limits at the end the artist's creative vision. That's why there is a huge interest on automating this task. However, best automatic approaches professional usage.
Sorry, Hernan, you were cut for the last 10 seconds. Yeah, sorry.
Maybe it's maybe it's my connection.
I think it's fine now. It's just maybe if you can repeat the beginning of the slide, that would be nice. Thank you.
The whole beginning, okay. But linear colorization is the process of adding visually pleasant colors to monochromatic line drawings. As you can see in this example figure, where colors schedules are used to colorize a monochromatic line art. This task is mainly essential in workflows of many industries like animation and graphic designs. However, the process is time-consuming and currently is still done quite manually, which limits at the end the artist's creative vision. That's why there is a huge interest on automating this task. For professional usage or purposes. At the end, these automatic approaches, they suffer right now from issues such as color bleeding, color inconsistency, and usually the interaction with the user is not straightforward. Recent approaches on automatic linear colorization has focused mainly on deep learning techniques, particularly on generative adversarial networks, also known as GANs, mainly due to its good generation of high fidelity images. categorization into categories based on their interaction. It can be a reference base or a scribble base. The first one, the idea is to transfer a particular artist style from a reference image color to the line art by searching similarities between them, as in this example here. The second one, the scribble base, the idea is that the user inputs some color scribbles, color hints, in order to propagate across the line arts. Although it is true that GANs can produce high fidelity images, these architectures can be unstable to train and sensitive to perturbation, or also sensitive to external interactions, which could produce perceptually unsatisfying results, as we can see, for example, in this image or in the hand of this result. Although it is true that the GANs can produce high fidelity images, obviously, as I mentioned before, we can see in the figure. I don't know if it's okay, the connection is perfect. Or?
It's working okay.
It's working okay. It's because
but if anyone experiences issues in the call, please reach out to me. But for me, it's working right now.
Okay, perfect. Sorry. So apart from these limitations that GANs can produce on the results of this diverse line characterization, recently it is shown that a new family of models called diffusion models have the potential to overcome these GANs issues and can surpass image generation tasks. So what are these diffusion models? So these diffusion models are new generative models, new family of generative models that transfer input data through a series of controlled noising and denoising steps to predict new data distributions, as is shown in this small diagram. So giving an initial image x0 from the real distribution, as shown here, the diffusion process successfully adds Gaussian noise. So this is called the forward process. And this noise basically has variance and mean controlled by a variance schedulers. In this case, it's called alpha bar for each of the steps, for each of the from t-1 to t to x big T in this case. And the idea then is to reverse the process by means of an iteratively, just to reverse this process by means of an iteratively denoising by means of an iteratively reverse process. So how this reverse process work, or is the main baseline of these diffusion models, is by learning a parametric approximation from x big T to the unknown distribution of x0, going from the noisy data, going back to the unknown data or the predicted data scales. So this parametric approximation that we need to achieve from going to x big T to x0, in the diffusion models, we can approximate it by a neural network. So the neural network, basically in the diffusion models, in this case is called epsilon theta, is trained to learn the forward distribution, to then during inference, the aim is to reverse the Gaussian diffusion process through a reverse Markov change. This reverse Markov change take into account the immediate, this change take into account the immediate xt-1 to produce the x0. Sorry. For this reverse change, basically we train a denoising network, which is epsilon theta, and then apply iterative refinement step on, for example, in this case, xt-1 to predict x0 of the unknown data distribution that we learn from the noisy forward process. However, in this case, as you can see in the image, baseline diffusion models were presented in unconditional mode, meaning that the network will generate images from pure noise. In this diagram is trying to show in somehow the training process, but normally in inference we have pure noise in the input data in the unconditional modes. Our idea then is to add control over the structure that we are generating at the end and the color, as well as the color, by coupling an implicit and explicit conditioning strategy. So in unconditional mode, we are generating line arts, illustrations, and in our case, we would like to generate the structure of this line art and also the color, the color. So then our proposal is jointly used two approaches to condition or diffusion models. In this case, the explicit conditioning in the purple block and the implicit conditioning in the yellow block. So in the explicit conditioning, the network receives a noisy image and the liner as input. Then by this approach, the network is forced to learn the structure of the liner. And also at the same time, we noted that helps convergence times in training. In the second hand, we have the implicit conditioning, where the user inputs some colors scribbles and the liner for then train specific encoder G theta that extract features colors from the scribbles and then inject it into the main pipeline of the generation of the generated network. Sorry. We propose these two conditions separately as a way to divide the two different tasks. So the explicit conditioning focuses on the denoising generation task and the structure of the liner, and the implicit conditioning focus on the colorization task. At the end, the framework is jointly trained from scratch using the L1 loss. In terms of the training setup, we use 200K color illustration from the Damburu datasets and 13K illustration for testing. As a matter of fact, from the dataset, we have colors illustration, as I mentioned before, but we don't have the lineouts. So we rely on two methods for extracting synthetic lineout. One is called sketch keras, and the other one is called sketch simplification. As a matter of fact, that documentation. Finally, we simulate human scribble for by randomly sampling vertical, horizontal, and diagonal lines. I'm showing both images in the bottom. Also, we control this scribble by sampling from the uniform distribution 3 different parameters: the number of scribbles, thickness, and length. Pass to the qualitative results. In this case, here we compare with two other deep learning methods, both using GANs architectures, one called ALAC-GAN and the other one's called PaintStorch. The idea here is we input to all of the three methods, the line art and the scribbles by the user, and the idea is to propagate the scribbles across the line arts. In terms of results, we present more consistency on colors in the eyes in comparison with the first method, for example, in the clothes in comparison with the other two methods, and in the hand, we can see color bleeding in this part of the hand with comparison with respect to the cloth, and in here some of the fingers are badly colorized. This is other results, same as before. We input the line art and the scribbles, as basically our method produces more consistency on color tones in black, so generating shadows in well placed across the liner, which translates in a more appealing visual colorization in comparison with the two other methods. We also present some quantitative results. We compare with 3 different metrics, SSIM, LPIPS, and FID. Mainly our results outperforms both methods in the first two, SSIM and FID, the first and the third one. And in terms of LPIPS, it surpassed ALAC-GAN, but it achieved comparable results with PaintStorch. We did also a small abbreviation study. Basically, we instead of having these two conditioning separately, we remove the implicit conditions, so the yellow block, and we concatenate, or we input also the scribbles onto the explicit conditioning blocks. And at the end, it results in a reduce of performance in comparison with the full method. Obviously, our proposal have some limitations as well. As we can see, when liner presents different structures here in the eyes, so the right eye and the left eye are quite different in the liner. So the network tends to colorize it in different ways. Obviously, it will be solved obviously if we add some scribbles in this specific part of the eyes. But obviously, the idea is that the network could also automatically colorize depending of the regions, on the nearby regions, in the correct way. On the other hand, for example, in this part of the finger of the hand, this is not completely colorized. So we could assume that this discontinuity could be presented to the object here. So this part of the hand is not well colorized as in the quite white, let's say. So these are some limitations of our proposal. And let me finish with the conclusions and perspectives of our work. So we propose a novel approach for user guideline authorization. We introduce this coupled conditioning with promising results on structural generation and accurate representation of color shades. Our method also prefers quantitatively and qualitatively state-of-the-art, these two state-of-the-art methods. For the future work, the idea is to also improve generation time using, for example, latent embedding, because right now we are using, let's say, the baseline DDPM, which basically for generating one image, which takes like 20 seconds. So it would be really helpful to starting introducing, for example, this latent embedding. And finally, we would like also to explore recent approaches for creating synthetic colors scribbles, because there are not a formal way of creating these synthetic color hints. Thank you for your attention, and if you have any questions, don't hesitate to ask them here or in the poster session.
Okay, everyone, we will start with our workshop. Julia, would you like to start?
Yes. Welcome back, everyone. Can you all hear us yet?
Yeah, we hear you.
Great. Yeah, I hope you enjoyed the beginning of the workshop. We will continue now with 2 more keynotes and 2 more orals. And yeah, I will now introduce the next keynote speaker. Unfortunately, so the keynote speaker is Ahmed El-Gamal. Unfortunately, Ahmed could not be with us today, but he gave us a recording. So yeah, we will watch the recording together. Ahmed received his PhD from the University of Maryland. He's now a professor at the Department of Computer Science at Rutgers University, where he's also the director of the Art and AI Laboratory, which focuses on data science in the domain of digital humanities. His research on knowledge discovery in art history and AI art generation has received actually quite some international media attention, with reports from various newspapers such as the Washington Post or the New York Times and Science News, and also many others. So we are very happy to welcome Ahmed in this workshop. Unfortunately, as I mentioned, he cannot be with us today, but he kindly recorded this keynote talk for us, and I hope you enjoy the recording. So I will start playing it now, and if anything is the matter on Zoom, please ping me in the chat, or if anything is the matter on site, please Ziad ping me. All right, enjoy everybody.
Hello, everybody. Thank you for inviting me for the workshop. Unfortunately, I couldn't be with you today due to travel. So I am recording this and sending it to you, and hope you enjoy this talk. If you have questions, you can always reach me anytime. Today, I'm going to be talking about AI art, the gains and losses we have been making in the last few years. I'm not going to talk about my research in particular, but I'm just going to start by briefly describe what I have been doing before I talk about the topic. So at Rutgers University, we have the Art and AI lab that I started more than 10 years ago, looking at the intersection between art and AI, how to advance AI by looking at art, and also how can we use AI in making art. There are many things we have been working on, understanding art, looking at building computational models for discovering artistic influences, and models for understanding creativity and understanding the evolution of art over time. We basically work both on the analysis side of art history using AI and the synthesis of art using AI. That let me just right away jump into the topic of today, which is AI art and how artists perceive using AI in art making and what we are making. Obviously, with any technological advances, artists take notice and use this technology in making art, and AI is no exception. So we basically, from the time of cave art and using tools in making some sort of art early in human history, to the discovering of paint and making paintings, to discovery of cameras and making photographs and digital art in the last 50 years, and AI. With every technological advances, artists always take notice and use these technologies. And usually that means there are more and more ways to express yourself as an artist. There are always more and more artists as the technology evolves as well. So AI is no exception. With the early days of using AI, some artists have taken notice and used AI or try to use AI in making their art. The most famous example is Harold Cohen, who used AI in making his art. And obviously the AI that was used at the time was very different from what we are using today. It was mainly rule-based systems. Another example is artist Lillian Schwartz from New York, who also have been using AI in her work early on. Here's an example of Harold Cohen works from the 80s. And it's really a very interesting work because it really shows what the artist is using AI for in the work. The artist is really interested in the randomness and surprises we get from AI completing certain lines and choosing colors. So that's very important in how we proceed today. So here came generative AI. So GAN appeared in 2014, and we could generate images of very small 32 by 32 images with GANs. Then came DC GANs, and with the power of convolution, we can generate 64 by 64 images. Images are not that good quality, obviously. There was lots of artifacts and uncanny looking images. Then Style GAN shows us basically how to generate 1 million megapixel images in a photorealistic manner, also with controllable attributes of the images. And by no means I wanted to be here comprehensive in looking at the history of image generation. Back in 2019, if you look at GitHub and search GANs, you can find there are 53,000 paper or code available using GANs or variation of GANs at that time. And now the number is doubled, obviously. So there are many contributions have made to this area, which you all know of. My goal is really to understand the use of these tools in making art. So in 2021, DALL-E came around, and DALL-E with other papers at that time shows us the power of adding language to image generation. So by adding a language and doing cross attention between language and image during the generation, the quality of the generation improved a lot. Then came Stable Diffusion and DALL-E 2, which shows us basically the power of using diffusion models in this art generation in conjunction with the power of training these models on billions of images. So great progress, obviously, from generating 64 by 64 images that are really crabby to generating photorealistic or illustrative images that are high quality, high resolution with high fidelity. So great gains definitely here. But what we lost in the process and where we are. So I'm going to discuss gains and losses. So obviously we have gains in resolution, in having high fidelity images, getting out of the uncanny valley, and using text as a descriptive way to generate images. But on the other side, I want to discuss a couple of issues here, two issues. The public perception of using AI as a way of making art, and AI art in general, some ethical issues, the issue of art's identity, the issue of the uncanny valley and how that's affecting making art. And some of the text prompt limitation, although this is a topic of a whole talk by itself, and the issue of controllability. So let me start by discussing this. And during my discussion here, I'm going to talk about results from two surveys we done with artists. So back in 2019, we have a survey of artists using AI. In that time, obviously, it was mainly GANs, and these are at that time some of the early adapters of using artists using AI in their work. And this year we have another survey that we haven't published yet, that we asked 500 artists using text to image to understand what are their feedback about using these tools. So let me start by looking at GANs, early GANs, and the kind of aesthetics that we get from these GANs. So here in the top, I'm showing a typical generation of a GAN when we train it on classical portraits of art portraits. And obviously GANs at that time generated this kind of very deformed, uncanny looking portraits. These portraits actually remind us, obviously, with some of the work by Francis Bacon in the portraits in the bottom here, with a fundamental difference, which is Francis Bacon has the intention of making this deformation to reflect on the person, on the portrait of the person, and to say something about it. While here, obviously, the machine failed to make a portrait similar to the data that we give it, and out of that machine failure came the interesting aesthetics that captured the minds of the artists at the time. So now we progress to a different kind of aesthetics. So definitely with recent advances in AI, we got out of what's called the uncanny valley, and we can really generate very high quality figures in the images. And now the aesthetics of machine failure is not the main source of aesthetics in image generation. We don't generate these kind of images anymore, which might be a good thing if you are making illustration or making comic books or making graphics. But is it always a good thing or not? Let's discuss this. On the other hand, constructive text-controlled generation has its own aesthetics. So here, the interesting images comes from really writing a very involved text prompts that combine or try to merge unmatched keywords, which can result in very interesting generation of images, and has its own interesting aesthetics like that. So the very different kind of aesthetics between early GAN-based model and recent diffusion text-controlled based models. So let me talk about the public reception of AI art. So in the early days of AI art from 2017 till 2020, there was really a good welcome in the art market and the artist community about AI art. So we here at Rutgers have built ICANN, and AI artist basically that has shows from 2017. In 2018, the group Obvious have an auction of one of their pieces at Christie that was sold for $350K. ICANN have been exhibited in art fairs like Scope Miami Beach and art galleries in New York, artists like Mario Klingman have some of his work auctioned in Sotheby's in 2019. The Barbican Center in London had an exhibition of different AI artists in the summer of 2019. The National Museum of China had an exhibition that involved several groups of AI artists back in late in 2019. And obviously the media coverage over these, over what's happening in AI art in these few years has been very positive at that time. Moving forward to today, we see things like AI groups banning AI art. So here's a news. Obviously, I've seen this and many others like that last year, where art communities start banning AI art completely. If you go to Reddit now and go to artist communities, many artist communities banned any AI art. So why is that? So today's obviously prompt-based models are pre-trained on billions of images taken from the internet without artist consent. And with this comes basically loads of copyright issues. However, this is not the main reason for that kind of backlash against AI art. It's one of the reasons. But this copyright issue is a huge issue now. And you heard in the news, obviously, about lawsuits against companies like Stable Diffusion and Midjourney, where artists are suing them for copyright infringement. So from this article in Art in America, I'm quoting here, the training process, which is diffusion, is suspect because it requires images to be copied and recreated as the model is tested. This alone, the lawyer basically argue, constitute an unlicensed use of protected works. So basically, since in Stable Diffusion, as you know, the loss function involved reconstructing the images in the data set. So basically, the lawsuit here saying that that loss function is unlawful because it's basically unlicensed use of these works. On the other hand, the companies, Stable Diffusion and Midjourney, are pushing back and arguing that in these cases there is no specific works that have been flagged as copyright infringement. So basically, obviously, this is not the last lawsuit that will come around, and most likely these lawsuits will be dismissed, but they're not going to be the last ones. It's going to be more and more of this, and these issues is going to stay with us for a little bit. So AI went from being a welcome tool for artists to kind of unwanted and banned and sued tool. Why is that? So copyright is one of the issues, but not the only issues, not the only issue here. So let's look deeper. So let's discuss the issue of AI and artist identity. So what is that? How the identity of the artists themselves can come through when using the same AI tool. Very fundamental thing in making art is the artist's identity. That artist basically has his own way of making art that identify him different from any other artist. So how this can become the case when you are using the same AI tool? How can the same AI be used by different artists and yet their soul and artistic personality can shine through the layers of biases existing in the data used in to train the AI models? Understanding this issue is very fundamental in accepting AI as a medium in art making. And actually, this issue has been raised before in the 19th century when photography came around, and there was a debate about whether photography is art or not. And here actually is a particular case in the court, basically where artist Mayer and Pearson sued other photographer for copyright infringement. And the problem was that the court said that photography is not art, so it cannot be copyrighted. And it boiled down to really proving that there is something really unique about the artist's way of using photography that capture their soul and personality different from other artists. So here I'm quoting from Aaron Sheriff's book, Art and Photography. For photography to be considered an art, it became necessary to settle the question of whether or not it was possible for the photographer to manipulate his medium in the way that a painter could his. So I find this quote is really fundamental. If you replace photography with AI art, that same statement holds. That's really the main issue about art's identity that we're missing today. So to dig deeper, if you look at the artistic process in using AI in making any art, what is it? What is the artist's role? So we have an AI model at the middle here, and the artists put some inputs and tweak the model and generate lots of images and do some sort of a post curation. So the artist's role is involved in this process from beginning to end. However, that depends on what kind of model you are using. So in the early days when you are using GANs, that was a very complicated process because the artist has to pre-curate a collection of images, choose the GAN model and tweak the parameters, generate lots of images, post curate these images. So it was a total involved process that the artist really is in control of the whole process. And obviously this kind of process, when the artists train on their own images, there is no issue of copyrights as long as the inputs images of the CR are not violating copyrights. And usually the output are transformative enough that it doesn't really violate copyrights as well. And the artist's identity here is clear because as an artist, you choose what to give as an input to the model, and whatever is generated is really a function or a derivative of these inputs. So there is no issue about the artist's identity. So artist's identity was really, really clear. Then when it comes to the era of big models, this era started with things like big GANs, where the model had been trained already on millions of images. And now artist's role is mainly playing around with knobs to search a big latent space to generate an image. So here comes really the issue of artist's identity. What is the artist's identity here? My role as an artist now is just searching this space, just playing with knobs. So that led to some copyright problems, not just copying the data set. The problem is that two artists, here is an actual example where two artists on two sides of the earth, one of in America, one in China, generate almost the same image. And now one of them try to sue the other about, or at least claim that it's a copyright infringement. It is a problem. None of them created this art from scratch. Each of them just mined these big GAN models and played with the knobs to generate almost identical images. So here is the problem that we're facing with now. Obviously, this is the same with text to image. Here's a quote from an article I wrote for the Guggenheim Museum blog last year. Does the use of AI preloaded with content reduces the role of artists to curation and playing around with knobs, which although deceivingly allows artists to mine through an apparently infinite choices, fundamentally limits expressing their identity. So I'm posing this as a question. So the same issue exists with text to image. As an artist now, your role is just write down or engineer basically a text prompt that control the generation. So what is it that you can control here? What is your artist role? So imagine this now, if two artists entered in the same exact prompt, obviously it's a very low probability that the system will generate the same image because the generation is based on a seed, random seed. So that's mainly due to no action from the side of the artist. It's due to the two random numbers being used to initiate the generation. The different outcomes are at the mercy of the random generator in the system. So the artist's identity here really boiled down to just random chance. So here is the problem again. So these kind of models, text to image model, really kind of wipe out the artist's identity. The artist's identity is really deceivingly hidden in reverse engineering the system to write out a text prompt to generate something interesting. However, at the end, this is mainly mining the system for generation. So let's talk about text prompts from the artist feedback point of view. So basically, text-to-image model improve the generative ability of AI model and help them to make sensible figures. That's really a good achievement. However, I claim that text prompting limits the generative AI models, and because basically Pixel is rendered only through the lens of language. So we concluded a survey collecting responses from over 500 artists who used this text-to-image model to understand what they think about them. 46% of the respondents found that such tools are very useful in their work. 52% found them somehow useful but could not integrate them to their workflow. And 22% find them not useful at all. When we asked them about the main limitation, they found out they all pointed out to lack of control. It's really hard to control these models using text prompts. On a scale of 0 to 10, the average score for controllability of this model was about 4.5. 50% of the respondents think the results are interesting, but not good enough to be used in their practice. How these tools will affect the artist's practice, we asked the artist. 90% of the artists surveyed think that such tool will affect their practice. 46% think they will affect it in a positive way. 7% think they will affect it in a negative way. Only 1%, 1.5% of the artists think that this tool will kill their practice, which is a good news. A good news is that it will not kill their practice. Now let's me try to wrap this up by what I think is the difference between making art and making images. Looking at this amazing painting by Picasso can tell us a lot. So Picasso made this artwork in 1907. It's known as the Ladies of Avignon in English. So in 1907, Picasso tried here to deform the figures, starting to what later became Cubism. This work was now is well known and well established at the very early beginning of Cubism of Picasso and Prague. However, at that time when Picasso made this painting, it was totally rejected, even by his close circle of friends and other artists. Even later, in 1915, when Cubism became a big thing at the time, that art was totally rejected. So when it was first shown in 1915 in an exhibition, it was deemed to be immoral by some critics. Even artists like Matisse didn't like it at all and think it's very immoral and unacceptable. Later, in 1930s, when it was put in the MoMA, the Museum of Modern Art in New York, then that's where basically it started receiving some acceptance and recognition. And 100 years later, interestingly, there was anniversary of this painting, and still the journalists who talk about this painting talk about it as being shocking and still very, very controversial. So what are we looking at here? Really, this is a good example of how art is being made. Here is the explanation from psychology of aesthetics. This is from a theory by Colin Martindale. And his theory is really explained that the progression of art is really made by artists by pushing against habituation. If you keep looking at the same kind of art again and again, you get bored of it. So as an artist, you always have to push against habituation and try to have something interesting and new and novel in your work. However, this has to come in what's called least efforts. If you do something totally shocking and surprising like that, it will fall in the negative part of this hedonic curve, which results in people rejection. So art has to really find some sweet spots of innovation and creativity to push against habituation. This is a long story, but really this is what was going on in early GAN systems that artists has been welcoming a lot. The fact that the machine generated this kind of machine failure aesthetics was really very interesting to many artists, and that was one of the reasons why artists really was very interested in using AI in making art. give them very interesting ideas. This might be the reason behind the well acceptance of AI in making art by main venues in the art world, like auction houses, art fairs, museums, and other in the early days. Nowadays, obviously, the kind of aesthetics, as I mentioned now, are very different. It's not that machine failure, it's mainly more constructive text-controlled aesthetics. However, in our early study, that when we surveyed artists back in 2019 about the use of AI art, I think that's very important here. We asked artists about what do you think about the use of AI in their work, and artists understand AI as a major impetus to their own creative process, in allowing them to generate lots of images very quickly and suggest new paths of manipulation and disruption of data to create images. For them, it's a vital step in leading them to seeing their own work differently. Here, they are talking about mainly using GANs and feeding GANs their own images. Basically, artists describing the relationship when using AI as a partnership, believing there is a real value and potential in pursuing this partnership model. And in their mind, the biggest gain could be found in two things. And I think this is the bottom line. Artists use AI because they find it to give them creative inspiration, new ideas, new visual effect that they didn't think about, and the creative volume aspect of it, which is basically the fact that you can create many images very fast in the process. So the question now is where we are about these two things, the creative inspiration and creative volume. Are these new models that we are making now, using text to image and others coming in the future, allow us to have this creative inspiration and creative volumes available to artists? These are the two things that artists are mainly looking at. I will conclude here that AI is getting better in generating images, but maybe it's coming to be less useful in making art. Thank you very much. If you have a question about this, or you want to discuss this further, you can always email me. Thank you very much.
All right. Can you see me? Yeah. Yeah, that was quite an inspirational talk, especially in light of now all these large language models, which are sort of similar with text, maybe instead of images. All these questions about copyright and fake and copies and so on. This is going to be quite the future. All right, thank you very much. I hope you enjoyed the recording. I would like to pass on now to my colleague Loris, who is going to introduce the next keynote speaker. Loris, back to you.
Thank you, Julia. Yeah, can we try if we can sharing screen? Yeah, so we'll keep sharing my screen. So people see your slides. We just want to make sure that they hear.
Yes. Great. I hope it was already. So we as a field have been evidently working on generative models for quite a while, and we know that there's this classic dilemma. On the one hand side, we evidently want to create visual works with great quality, and generative adversarial networks are a great example of that. On the other hand, you want to cover essentially the entire landscape of all the images and have a system that's capable of generating essentially everything that's possible. VAE is being an example of that. But you have this trade-off. GANs, great quality, but they suffer from mode collapse, so just give you a tiny chunk of your distribution, or you get the great data coverage, but then you're losing on the quality end on the other end. Recently, powerful likelihood models, such as autoregressive transformers or diffusion models, came around, and they start to bridge the gap between both ends. They're score-based, meaning they're open to arbitrary network architectures that you couldn't go for. You're not having this partition function anymore. You have the stable training finally, no adversarial minimax optimization like in generative adversarial networks, but they're still costly. And what I mean with that is, I guess here we're pretty much aware of like diffusion models and the training paradigms. So I'm just skipping over that. But what I mean with like costly is, I guess that's the artistic part of it. It's recovering. That these models, powerful as they are, these power that they have actually is kind of also as a curse for them. They try to home in on any tiny bit of the data distribution and get any tiny hump there in this distribution right. And with that, they will focus on the majority of the imperceptible details. Yeah, there's a lot of things which are imperceptible right now. I'm waiting for my presentation to just transfer over the Wi-Fi. Yeah, so most of the things that the model will actually concentrate on and spend most on the bits on are things that you and I would not care about, like the differences between these images on your right there. Images which to us are not noticeable. And compared to that, very few bits are actually allocated to semantic details that you and I would care about, like with the gender of the person, whether the person is wearing glasses, the length of their hair, and the like. How can we make sure that the model actually spends more bits on what we care about, the semantical details? Now, the brute force approach would be actually that you just ramp up the number of bits in your model overall, which means like you just increase model size. And with that, you eventually like push this entire curve towards the top right. And the model will, with that, also allocate, by the way, more towards your green area, your semantic details there. That's what I'm talking about. The alternative approach, and that's what I really want to get into, is actually have the model focus on the details that actually matter to you and I, on the semantic details more. And that's where we've been going with stable diffusion. So our goal was to democratize image generation, in particular the research in this field. So how can we render smaller models more effective? That means we want to have them being powerful, but at the same time, we also want these models to be accessible. And with accessible, I mean not only that we release them open source, we released stable diffusion open source when we delivered that, but at the same time, we wanted these models to work right from the bat on standard consumer hardware, meaning that they should work on GPUs, which you get for $300, $400. These days, they can work on a mobile phone. Yeah, but since you want to build this model so that it understands everything that's out there in the visual world, it means that you need quite a bit of training data. So how can you get billions of training images, hundreds of terabyte worth of training data fit into a mobile phone, which means like essentially take the entire internet and make it fit into your pocket? It means that you need to do a lot of abstraction. I believe that this is the pinnacle of artificial intelligence, really our ability to abstract and throw away the details that you don't care about and just concentrate on what really matters. And that's where we've been going, really doing this massive compression. For that, we then assumed that we have a generative model, for instance, in that case, this UNet architecture that slowly transfers over to that screen there, where you can take random noise, take this UNet architecture and turn that into an image of the dog there, top left. But we are not doing that directly from the noise to the image, but rather suggested a two-stage approach. A two-stage approach, which in the first stage essentially does perceptual compression. Essentially learns to just focus on the details that matter to you and I, and have this generative model. There we go. Have this generative model. It's just interesting that it's going back and forth. I thought, like, when you have little bits, you're just happy with what you've transferred. You're not taking it away and rebuilding it. Oh, getting there. Whatever. With that, have the model concentrate on just the details that you actually would want. The benefit of that, when my slide finally transfers over, is that our powerful likelihood model can now concentrate on the long-range interactions, the semantic details that we actually care about. And this first stage, which is very efficient, a convolutional architecture, takes away all the local details that you don't want to bother this complicated model, the powerful likelihood model, with. So essentially, we utilize the inductive biases of the CNN, local receptive fields, to take away and model the local details in the first stage by means of this encoder-decoder architecture there. And then our powerful likelihood model operates in the latent space of this representation there and has to just work in this latent space. So all the details are taken out by the first stage, and then the likelihood model can concentrate on long-range interactions. With that, you get an approach. We simply type in what you want to see an image. I want to see a photograph, mountain, tree, lake, highly detailed, photorealistic. And much faster than this slide is actually translating, the system is then generating images, really much faster than we see here. That's actually a miracle. Generating images much faster than transferring it from here over to that slide. I thought that this would work with the speed of light, but apparently the generation is much faster than the data transfer here. Interesting. In that amount of time, we would have probably already generated 10 images with that system. Probably making a new benchmark. There we go. Yeah, and you get this in much shorter time than it took to actually translate over, just a few seconds. You can also, and that would here be my point. As a layperson, a non-skilled, not artistically gifted person, I would be happy with that, just typing in and the system doing the rest of the work. As an artist, as a designer, you would want to have more control over what you're generating. And for that, something like this here is probably beneficial, where you can really to the pixel say what you actually want to see. Like top right, you give a semantic segmentation map, and you say like you're interested in actually having sky there should be water, there should be trees, and whatever else. And once this slide finally translates over, you should be able to see that this is like 3 times the same scenery, but if you just say like, I want to see trees there, I want to see clouds there, whatever, there's evidently a zillion times different cloud configurations that you could come up with. This is a stochastic approach that at the end of the day can then sample for the same rendering different visualizations, different ways to actually put exactly the same spatial configuration together. I hope you appreciate like artists, skilled persons would probably appreciate something like that more. There's now plugins based on Stable Diffusion for Photoshop, GIMP, Blender, After Effects, and so on, and approaches like ControlNet, and lots of papers at this conference building on top of Stable Diffusion and tuning that in different directions, which I believe might be very helpful for artists. Somewhat artistic here. Yeah, let's move forward. So far, I've shown you how to take these powerful likelihood models and learn with them more effectively. I want to push this a little bit forward and ask really what we should learn at all using our generative models. Yeah, not just how to learn more effectively, but what we should be actually learning with these models at all. And with that, I mean that if we look at artists and how they're actually going about, let's take Monet in this particular case here. When he was painting trees, he was actually going out there and looking at trees. Now, he was a gifted artist. Why does a gifted artist need to go out and look at trees when he's painting trees? Doesn't he know what trees are looking like? I mean, like Ronald Reagan so infamously said, a tree is a tree. Like, how many more would you actually need to look at? And still, it kind of makes sense, right? Because nature gives you an infinite amount of variability. And that's what he was actually using as a source of inspiration. Contrast this with how we are training our neural networks. We're stuffing all the training data into these very precious parameters, these very costly parameters that we have there. We essentially try to learn all of the training data by heart. Wouldn't we want to have more an approach which can then online during inference? Just look at the world out there and utilize that for synthesis. And this is a paradigm shift, kind of a backward future, because Ayosha and others have been doing this already 20 years ago, but in a different context. This is a paradigm shift that I would advocate for here. Don't learn to represent these local details in a generative model. Instead, utilize a database of patch examples. And then during inference, look up the relevant details that you care about from this database and synthesize conditioned on those samples that you've retrieved. So you try to do not everything out of the neural network, but have the neural network look at the database as it's synthesizing and using that as a grounding. And with that, the powerful likelihood model can actually concentrate on what it's great at, the composition of the scene, and does not have to memorize all these local details. Training, you take the data and learn to reconstruct the data, and in between is this likelihood model that does the reconstruction task. But I hope you agree that when you try to reproduce your data, it's actually quite beneficial if you could condition this synthesis part on related samples. So when I'm trying to paint this eagle down here, I guess we all agree that having these patches here, these nearest neighbors at hand, is probably very helpful when I need to paint this eagle there. And the same thing we're doing here, we condition the synthesis process on the nearest neighbor patches. During inference, you're then provided a database, but this does not have to be the training distribution. You actually don't need this. You can utilize an arbitrary different database for that, and then retrieve related samples from this database. You can actually utilize different retrieval approaches based on nearest neighbors, based on some text prompts, whatever else that would be. And then as you do synthesis here, you condition on the retrieved samples. Now, the beauty of that is that I can train a model on, let's say, ImageNet images, and then during inference, I actually condition it on patches that come from a different database. For instance, something artistic, wiki art. This model during training knows nothing about art, has never been trained on that. And during testing, I post hoc, the model is frozen, nothing tuned there, zero-shot manner, transfer over from ImageNet to style transfer by simply swapping the database that I'm retrieving patches from. I'm not changing any model weights there. I'm just swapping the database and say, like, when you want to render something, take the nearest neighbors now from a style database, and your model automatically does, as you see here, a stylization renders artistically rather than photographic as we've seen before. You might wonder, is this not costly? It's not. Nearest neighbor retrieval, thanks to the scan library, is super fast, 100 milliseconds, you get your nearest neighbor patches. And with that, you actually get a 10-fold increase of speed because your model sizes, which you see here towards the left, get significantly smaller models, and then improvement in speed. So in short, don't learn to learn all of these samples in your powerful likelihood model rather than utilize retrieval augmentation that leads to smaller models, improves their performance, and has the likelihood model concentrate on what it's great at, the composition of the scene, and it also allows for a very efficient, convenient post-hoc transfer. With that, the last bit I want to show here before I really go and say a few words about the arts is a word that we called iPoke. And our question was, can we take a static image like this one here and just pull or push an individual pixel, this individual flower there, and then have the model synthesize how the overall flower would behave, how it would dynamically move. So essentially give the user a mouse and drag an individual part on the body of this person there, and then synthesize different options how this person could behave. There's evidently not one, it's an underdetermined problem. If I'm just plucking an individual pixel, there might be different movements, which you should see here when this slide's building up. The model should be able to generalize to different instances, different persons, And it does not have a body model or anything. It's just learning that from the pixels. So you can run this model on arbitrary object classes and essentially learn their dynamics, the kinematic interdependencies within objects. If I pluck or if I move an individual part on my arm, how would other parts of my arm in that case move? Like learn these interdependencies and generalize to novel instances in that case. Just in a nutshell, how that works, the user is providing an image and is providing this individual mouse drag here on an individual pixel or several pixels for that matter. And you would want to map this over directly into the image domain on frames. Now, evidently, we cannot directly link this up with a decoder and synthesize videos, because there's unknown interdependencies between this one pixel that are moving and all of the other pixels. And for that, we suggested to utilize a conditional invertible neural network, a bijective mapping between what we want, the video representation, and this latent kinematics that we need to learn that we don't know about, which essentially tells us how objects are moving. If you had this, then we utilize a recurrent architecture here to take these individual frame representations and render the video. And for training to really get this, you're taking a video sequence, you're encoding these individual frames, and then because there's a bijective mapping, you can turn it around. You take these individual frames and want to map it onto this latent kinematic representation conditioned on the site information that the user provides you. And then you can back and forth and try to reconstruct exactly those frames. That's a training target. Long story short, with that, you're provided an interface where you can move an individual part of the human body, for instance, and it then just exactly that. You can take a potted plant and drag individual leaves there and animate them not just once, but should see this, whatever. Then get different renderings of this potted plant, because evidently, if I'm just dragging an individual leaf, there might be different ways that it is actually moving. I guess you can faster imagine what's supposed to be on that slide than it actually shows. Dynamics is probably that thing for this link. Yeah, maybe you should see different ways that these potted plants are actually moving. Good. Let me try to wrap up here and make a few statements, which I believe are pretty much nicely placed at this particular workshop here, on whether this black box that we've been looking at here, our generative AI, can actually create art. Right? It's this digital brain in a box, so to speak, creating art. It's this art here. And I just use like 3 different things that we would actually attach to art. Like first, art needs to be artistic. Yeah, does that mean it need to be technical complex? Like is in that case, this scan rendered image where you just see part here, is this with that out of the window? Well, I mean, there's the iconic black square by Malevich, which is considered art. Yeah, very precious art to many of us. And so technical complexity cannot be it. Next thing, art needs to be beautiful. But then you have Beuys with this Fettecke, where he just took like several pounds of butter and just put them into this corner, which was also not convincing to everybody. Like there was a caretaker of this building who essentially removed this masterpiece. And this is the only thing that's left over from it. Probably there was too much of a stench, but the bottom line there of Dadaism, anti-art, Fluxus movement, and all of these was, it's the idea that matters at the end of the day, not that you and I consider that beautiful. Who are we? It's in the eye of the beholder. Next thing, third thing would be art needs to be original. I mean, other than that, a photocopy machine, which is supposed to be here on the left-hand side when it finally comes up. A photocopier, a Xerox machine would be a great artist, right? And facsimiles and so on would all be art that we're looking for. But what about this? This, which you're seeing here on the right-hand side, amazingly, you're seeing it, is evidently great art, and it is a painting. And if it were from Max Pechstein, we would probably all call it a great original, and so have done a lot of art critics. And they were willing to pay really hundreds of thousands, or in these situations, even millions of dollars for these artworks. It only later turned out that this was actually not Max Pechstein, but Wolfgang Beltracchi. My point here with the Beltraki forgings is these were original images. He wasn't just copying something. He essentially made up an entire part of an oeuvre of Max Pechstein and other artists. And that changed everything for the artistic landscape. Yeah, before they said like, great original work. It was original, it wasn't there before. And he just made up more and more images around so that it was actually becoming an oeuvre, and it nicely fit into what Pechstein, Ernst, whatever could have created. These are all original rendering. But the moment that people realize it's not Pechstein in the box, but somebody else, that changed things for us. So with that, I can only conclude with what Gombrich has said. There's really no such thing. Wait a sec. You're having that little bandwidth. Shouldn't you be happy with having all the pixels there? Well, as Gombrich said, there is no such thing as art. He said there's only artists. So what really matters is what's in the box, not the output of that box. With that, come to the Chinese room experiment and would want to say, like, if this box there is our computer or an artist, we cannot from the output outside determine whether this thing has any understanding and with that any originality. Yeah, just by having like somebody throwing Chinese letters in and then nice Chinese letters coming out. From the outside, this might look like this is an artist having understanding of what that person is actually doing, but maybe he's just following rules like our computers are doing. From the outside, we cannot determine it. And my point here would be that we as a community have been all buying into what's called weak AI. This is not meant negative against what we're doing. This is all fine. With that, I just mean that ever since Turing, our goal was the imitation game, trying to imitate human behavior, which is great. With that, you can solve a lot of problems, create a lot of value, build self-driving cars, chess-playing agents, whatever else. But when we, as we've just seen, want to have an agent that creates something original, that has some understanding about what they're doing and not just like dropping a bucket of paint as an accident. When we think that art is all about these intentions and whatever else is there behind that just shown, then that actually changes things. And the imitation of human behavior in that case does not guarantee understanding in that case. And we, as I've just shown beforehand, tend to actually value very high if we know the artist, and low if we think that that was just an imitation of somebody else. So let me wrap up this point here. We are obsessed with the originals, and we don't like these black boxes imitating those. We spend lots of time, money, and whatever else going to exhibitions, waiting there, even taking into account that our experience there will not be like this, but more like this one here, crowded scenes, where you would have a much better time probably sitting at home, looking at this thing at Google Arts or whatever else, being able to zoom infinitely into the scene, see much more than this crappy internet connection here sends over, yeah, and essentially seeing as little from this artistic work like what you're seeing here, yeah, and being then pushed forward after 10 seconds because the person behind you also wants to get a glimpse at that scene. Nevertheless, we do it. Why? Because we're obsessed with the original. And that's exactly my point. Final slides here. Better so. It actually matters to us who's in the box. And we want to have a human artist in this box. Because as Boyce said, every person is actually a bearer of very particular abilities, a self-determining creature. And he concluded so nicely, the sovereign par excellence of our time, and he called that an artist. A system like we've designed it, or other generative AI systems, I want to pretty much follow what I tell the system. It should be a tool, and tools should do what I actually want. If I build a hammer, it should do exactly what I tell the hammer and not knock wherever else. The artist here should be this self-determinant, this sovereign, yeah, that makes up what they actually want and not just follow a rule and follow my rule. And with that, my point here would be only when we have that, I guess, then we will appreciate that as being an artist. The rest may be a very helpful tool for us. That is taken clearly. And in the loop, together, the artist and the computer will also produce art, but not this zero stop thing where you just say create art and what comes out. I guess that with what I've just tried to sort of lay out here, we will probably not appreciate as art. So last slide. My understanding is that generative AI is an enabling technology, a very powerful one for boosting human abilities. You can take the untalented and with AI, with very simple approaches, one-step approaches, just text to image, enable creative expression for those who did not have it with limited artistic abilities and boost their potential. And you can take the professional and with generative AI, essentially with iterative approaches where the human then is in the loop with the AI and the other way around, image-to-image synthesis and the like. Turn this into a serendipity machine, something where an artist can very quickly see a lot of different renderings next to another and then get the different crazy ideas that they might have had distilled next to another and say like, hey, I want to combine this and that and that. And with that, it becomes a very powerful tool also for the professionals. I only see the value in augmenting human abilities, but not replacing them. So this automatic art creation, I don't think that that's where we want to go. We want to really augment the abilities of the layperson and of the professional. And then it's going to be a very powerful approach. And with that, let me thank you for your attention. Let me thank the internet connection for finally getting me through the next slides. And I'm happy to answer any questions.
Yes, Scott, yeah, more questions. Thank you for the talk. It was really interesting. I have a question about when you're using retrieval. So I was actually just at another talk that talked about using retrieval for video question answering, and they showed that you can drop out a certain fraction of the data set at training time and augment the remaining images only at inference time, and you don't see a notable performance drop. Have you looked at similar experiments or maybe mixing the train and test data retrieval databases?
Mm-hmm. So I've shown here examples where we also changed the database during inference. One interesting experiment that we've done in that direction was that we've observed that the larger the gap or the difference is between the database that you have during training or the data set that you have during training and that which you have during inference, the more gain we've observed from using actually retrieval augmentation, which kind of makes sense. In a scenario where you do quite a bit of transfer, you have a large domain gap between train and test. In that situation, it turned out that you get most gain from retrieval augmentation. When they're very close by, it's sufficient to just store everything in the training set. In that case, we observed a gain in terms of like speed of the model and the robustness, because then the number of model parameters can be smaller. But in terms of performance, you get most of the gain when actually you have a large domain gap between the two.
And as a small follow-up, is there a minimum size on the retrieval database? Is there, if I take 4 or 5 images of this room, I'm not going to have enough coverage of a distribution. Right?
Well, as I said, like you, for instance, go for these nearest neighbors. If your database is the samples that you have in there are too far away from the image which you want to reconstruct, because it's this conditional synthesis, the conditioning essentially does not provide you any mutual information with what you want to generate. So my point would be, it's not so much the number, it's actually the mutual information between the database that you're retrieving from and the images that you want to reconstruct. Evidently, if there's zero mutual information between the two, it's not helpful. It's not hurting, but it's not helpful. If there is a lot of mutual information, it's helpful. And that is what's mattered. Not so much the number. Sure, the more likely it is that there will be a high mutual information, but it's actually the mutual information that you're interested in.
That makes sense. Thank you.
Very good talk. I'm Alessandra Sara, Senior Director of AI and Data Science at Shutterstock. We have 400 million images from artists, more than 2 million around the world. So we care very much about protecting artistic creation and enhancing their ability in the professional class AI gen. We recently launched a generative model within our platform. So my question is similar to the previous one, going back to the nearest neighbor.
Yeah.
So you made a point that it's only 100 milliseconds more. That 100 milliseconds more for us is a no-go. We operate at below 100 milliseconds, which it means that it's not only these extra 100 milliseconds that we are talking about. Once you retrieve those nearest neighbors, you also need to encode them and pass it to the model. So there is this image encoder that also has to operate on the number of samples, which we will assume we can parallelize, and then send the information to the model for the generation and then back.
Now,
So,
I was saying just 100 milliseconds more because of the underlying generative AI that you have. If you ever played around with ChatGPT, you notice that there's typically a delay of more than 100 milliseconds relative to the time that it takes for this generative model to actually do its processing. These 100 milliseconds don't matter. If you're a regiment where these 100 milliseconds would be out of the window for you, I suppose that the generative model in the first place is probably too slow. Now, there are approaches to get this faster, reducing the resolution, going with our latent approach there for a much smaller sort of code book that you're going for, a much smaller dimensionality. With that, you probably would have an opportunity. But my point would still be, like, especially when you go for diffusion models, there are distillations of that, papers at this conference trying to speed them up, DDIMs and so on, doing that in fewer steps. But typically, like 100 milliseconds is already quite something. If that is an issue, then the generative model itself is probably small. Yeah.
They all work.
Yeah. Yeah.
Very fast. It was a brilliant talk. Thank you.
Is it okay? So yeah, moreover, each item has a product link. There is user likes some posted outfit and they want to get included item. They can click it and buy it. Here we can assume that if this posted outfit or set of items got a lot of likes, it would be a good outfit. In other words, we can regard number of likes as the goodness of set of items. So as I mentioned, the outfit is regarded as a set of items. And then by using this dataset, we can consider the fundamental problem, namely set-to-set matching. First, we have a set pair. Here, each set contains fashion items. That is, we can regard each set as the subset of outfit. Next, for this set pair, we consider to estimate the matching score or approximate the matching score function f. This score is based on the posted outfit by users. Then this problem seems that the estimation of goodness of outfits. Set matching problem is a number of applications like recommendation system or information retrieval. Even though set matching problem is essential for fashion data analysis, there is very few works to tackle this problem. Then we expect that all of you will be interested in this problem and seek novel and unique methods to handle this problem. This is one of the important sub-problems. But then when we handle the set matching problem, is it enough to consider the IID scenario? Of course, it is known that many machine learning algorithms assume that training data and test data are generated from same distribution. And this assumption is called independent and identically distributed assumption. Here, imagine applying machine learning approaches to fashion data analysis. If the training data is dominated by formal attire, while the test data is predominantly composed of cutting-edge outfits, what would be the potential challenge? This is certainly an extreme example, but addressing similar issues to some extent is essential. For example, if training data is old-fashioned or traditional, how can we handle a fad or temporary trend? All these problems are treated as distribution shifts or dataset shifts. Then our aim is to tackle set matching problem under the distribution shift assumption. So next, let's check some statistics of our datasets. First, as I mentioned before, our dataset is accumulated over a decade from 2010 to 2020. Total number of posted sets or outfits is about 2.5 million, and total number of items is about 15 million. On average, the number of items included in the posted outfit seems to be around 6. And the average number of likes per post is 27 and median is 9. And total number of unique users is 1900,000. Here is the sample items included in our dataset. However, as we can see that such statistics like average over a decade may not be useful since most of the figures are shifted. For example, in 2010, which is the year our social media was launched, we had only just under 300 active users. In 2040, the number of new active users peaked, acquiring 80,000 new users. Such significant shifts in user base are likely to sufficiently alter the quality of the data. So, of course, with the increase in active users, the number of posted outfits and the number of items included in them have also increased. In 2010, around 1,400 outfits were posted, and that number peaked in 2014, exceeding 4 million. From there, it gradually declined reaching around 80,000 in 2020. Furthermore, from the table, it can be observed that the number of likes on the post has shown significant shifts. It is clear that assuming the data to be IID is impossible for this dataset. Therefore, proposing new method to handle distribution shift is essential. So we introduce simple benchmark methods for set matching under distribution shift. Of course, there exist many methods to handle distribution shift, domain adaptation, or out of domain generalization problem. Then this is just a benchmark method, yet it is enough to show the necessity of distribution shift adaptation. So first, it is known that ordinal empirical risk minimization, or ERM, is effective under the IID assumption. That is, ERM can generate the unbiased estimator for the IID data. However, if this assumption is violated, in this case, trend distribution and test distribution are different, and ERM cannot generate unbiased estimator since the expectation of the average of loss function over the trend distribution is not equal to the expectation of original loss function over the test distribution. Here, we consider the importance weighting strategy. That is, we can prove that importance weighting by density ratio for the loss function on yield the unbiased estimator as ordinal ERM. To estimate the density ratio, we can use the binary classifier, which approximates probability of input data is from test distribution. So here is the experimental results for our dataset. One advantage of our benchmark method is it is applicable for arbitrary based models. For example, let's check the results of set transformer. Min IW and max IW are our benchmark methods, and each of them represents the weighting strategy. In this experiment, data from 2030 is the training dataset, and data from 2030 to 2070 are the test dataset. For 2030 as a test dataset, all of them are equal to the original ERM, and then all results are equal. For other test dataset, we can see that the performance of original set transformer decreases as shifted, and our importance weighting methods reduce the impact of distribution shift. This applies for other base models. So finally, let me conclude our presentation. First, we introduced that fashion data analysis consists two essential sub-problems, namely set matching and distribution shift adaptation. Both of them are essential and we need to handle them. Next, we provide the novel dataset Shift15M for set matching and distribution shift assumption. Our dataset is accumulated over a decade and includes several distribution shift properties. We also introduce simple benchmark methods to tackle this problem and show that the necessity of distribution shift adaptation. Finally, we provide the Python API for our dataset. So that brings me to the end of my presentation. Thanks for your attention and thanks for organizing great workshop.
For example, screen imagery links or images.
Yeah, investigating such specific shift type is feature works. So I expect that you can come up with novel methods to tackle this problem.
Hello, I'm Rohan Sarkar. I'm delighted to present our work on precise 3D shape estimation for diverse body types. This work was done as a part of my internship at Amazon. Our goal is to estimate body shape and pose. And for this, we fit SMPL body models to monocular images from which the pose and the shape of the person in the image can be estimated. Current methods, as you can see in the picture on the left, only work for certain body types and does not work for all body types, especially those that are underrepresented in the training data set, like high BMI body types. Before we present our method, I would like to introduce SMPL and prior work. SMPL stands for Skinned Multipersonal Linear Model, which is a vertex-based parametric model that can represent human bodies in a wide variety of natural poses. And it is parameterized by phi that captures the global 3D position and orientation, theta that captures the pose, and beta that captures the body shape parameters. SMPL is supplied with a linear blend skinning function SV that gives the 3D mesh, the 3D vertices of the mesh. There are two types of approaches that have been typically used in prior work. Those are optimization-based and regression-based methods. Optimization methods iteratively fits a 3D mesh to a sparse set of 2D joints, and on the other hand, a regression-based method like HMR directly regresses the SMPL parameters and the camera parameter. During training, they minimize the error between the projected joints from the predicted mesh and the annotated joints. Spin is a hybrid approach that combines the two types of approaches. It combines a prediction module and a refinement module. Like prediction module is something like HMR, and iterative refinement module is something like Simplify. It's trained in two stages. In the first stage, it predicts an initial shape, which is not perfectly aligned. And in the second stage, the refinement module is incorporated inside the training loop that refines the shape. The refined shape is then used as pseudo ground truth for training the CNN in the next epoch. During inference, only the trained CNN is used to directly predict the SMPL parameters. A major drawback of previous approaches like spin is that they focus on improving pose, but not body shape. As you can see in the examples, spin aligns the joints pretty well, and hence the pose estimates are good, but spin cannot predict the body shape accurately. Our goal is to adopt spin's hybrid strategy, but focus more on improving shape estimation, both in the prediction and the refinement stages. A straightforward way to improve body shape estimation is to collect 3D body scans of people. However, this is expensive and time-consuming, and hence difficult to collect 3D ground truth for a diverse set of body types. On the other hand, collecting 2D data is relatively much cheaper, and this allows labeling much larger in the wild datasets comprising of people with diverse body shapes. Prior work uses a sparse set of 2D joints or open pose key points, which works well for certain body types, as shown in the bottom left. However, as one would expect, it does not work for all body types, as shown in the example on the bottom right, as the 2D joints do not provide much shape-specific information. Some prior methods have used body silhouettes to accurately recover body shape. This works for 3D animal reconstruction and people wearing skin-tight clothes. However, for such silhouette-based methods, only the boundary of the silhouette guides the loss, and human clothing often corrupts the silhouettes, as you can see in the examples on the right, and hence body shape cannot be estimated accurately. A recent method, Shapey, collects body measurement data such as height, bust, waist measurements, and textual descriptions of the body type, such as long legs, skinny, short, and use these attributes for training. Our goal is to use dense pose for improving shape estimation for diverse body types. The key insight that we use in our work is to use dense pose that is trained using dense 2D ground truth to supervise the 3D shape estimation. We'll explain this with an example. For this image, we first run dense pose that aims at mapping all the human pixels of an RGB image to the 3D surface of the human body. Since only pixels on the body have 3D SMPL correspondences, the dense pose model learns to estimate the person's body shape under clothing. For each pixel, we find correspondence points on the 3D SMPL mesh, as shown by the red dot. We can then continue this for all pixels in the foreground for the person and get those dense correspondences. In this example, we show 5 such points. In our work, we propose a dense correspondence loss that promotes alignment between a dense set of per pixel mesh to image correspondences, and the loss is shown in the equation below. Our training framework is a hybrid approach like SPIN that we saw before. However, we focus more on improving body shape estimation, both in the prediction and the refinement stages. Let us now go through our framework step by step. For an image I, we first feed it into the CNN regressor to predict an initial mesh that you can see is not perfectly aligned. We then get the dense pose D, and we input the predicted mesh and the dense pose to our shape refinement module. The shape refinement module iteratively fits the predicted mesh to the dense correspondences using the iterative loss function, as you can see in the animation below. And then we take the final refined shape and use that to train the CNN regressor in the next epoch using another loss L regression. We now show some examples of how the body shape is refined during training. In the first 2 columns, you can see the image and the corresponding dense pose. In the left SMPL, we see the initial prediction, and in the right, we see how the mesh is iteratively refined. Here is another example, and it can be seen how the refinement fits to the body shape under the clothing. Here is another example. We introduce another loss named pose invariant vertex alignment loss. For this loss, we first project the predicted mesh in the T-pose, where theta t and phi t are the pose and the global orientation in the neutral T-pose. Similarly, we also project the refined mesh in the T-pose. The only difference is in the shape parameter beta for the predicted mesh and beta hat for the refined mesh. We then use the linear blend skinning function SV to generate the vertices, and the proposed loss penalizes the variations between the predicted and the refined mesh vertices in T-pose, that is after the pose effects have been removed. In our training framework that we showed earlier, we trained in 2 stages with the 2 losses, L regression for training the CNN and L iterative for iterative refinement. We now elaborate more on that. In the first stage, we train the CNN to regress SMPL parameters using the regression loss, which is sum of the 3D and 2D joint alignment losses and mesh alignment losses. Among these, the L3D joints, L2D joints, and L mesh were previously introduced in SPIN, and in our work, we introduced the pose invariant vertex alignment loss that I just mentioned. In step 2, we refine the predictions iteratively with an optimization framework using the iterative loss. The L priors was used in SPIN to avoid unrealistic pose and body shape estimates. And in our work, we introduced this dense correspondence loss for shape refinement. And we use the refined predictions to supervise the CNN. During inference, we use the trained CNN for prediction. Also for body types that are underrepresented in the training data, we run another pass of optimization with the iterative loss to refine the test time prediction. And this gives us improved estimates for people that are underrepresented in the training dataset. This stage 3 refinement is optional. In our work, we pre-train our network on the SPIN training datasets and fine-tune on the model agency dataset introduced by Shapey. However, we pre-compute the open pose joints and the dense pose maps and use them and do not use the body measurements and text descriptions that Shapey uses. We evaluate on SSP 3D dataset, which has 311 images of sports people with diverse body shapes. The metrics that we use are mean per vertex error in T-pose. The lower the error, the better, and mean IOU between the predicted and the ground truth silhouette. The higher this metric, the better. We now show some qualitative results. On the SSP3D dataset. The green SMPL meshes are those generated by Shapey, and the pink ones are using our method. From table 1, we observe that using our full method, we have an overall improvement of 17.7% on the per vertex error metric over Shapey. We conducted an ablation study and saw that our T-pose loss improves performance of our CNN by 2.6%, and stage 3 refinement improves performance further by 17.3%. And without the test time refinement step, our method performs on par with Shapey without using any of the linguistic or body measurement labels. Here are some qualitative results on diverse set of body types and in different types of clothing that we downloaded online. The green meshes are those generated by Shapey, and the pink ones are using our method. Here are some more examples. In summary, we propose shape-specific loss functions to improve quality of the 3D reconstruction on diverse human shapes. We introduced two such losses, the dense correspondence loss that promotes alignment of per pixel mesh-to-image correspondences, and the T-pose loss that promotes shape-specific vertex alignment by disentangling pose effects. We also added a refinement step that improves body shape estimation, particularly for body types that are underrepresented in the training dataset, like high BMI body types, and our full method improves by 17.7% over Shapey on the SSP 3D dataset without using any of the body measurements or semantic attributes for training. Thank you.
Thank you for your great presentation. I can deeply understood that your proposal can well up for the sports people with high diabetic process. But how does the effectiveness for the normal, for example, normal size person or extremely thin person or extremely unusual pose person?
Unusual pose, you're saying?
Or unusual pose person, right?
Oh, unusual poses. Okay, okay. Yeah, like our method can do pose estimation and shape estimation. So like unrealistic poses are like there are certain the prior laws that we introduce. If they like it can work on those, but it depends also on the prior losses that are enforced, the constraints that are there for those. But it should work on those type of like whatever spin can do, our system can also do. But our method improves the shape estimation, which was our goal. Thank you.
Everyone, that's conclude our workshop. I hope you enjoyed your time and wish you a great time at CVPR. Thank you very much.